Hey guys, BuildZoid here, and today we're going to be taking a look at a RTX 4090 PCB. This time it's the ASUS RTX 4090 Strix. This is probably one of the best RTX 4090 PCBs there is. The PCB pictures are from Tech Power Up's review of this card, so if you'd like more information about it, there's a link to the review down in the description below. Also, big thank you to Tech Power Up for providing high-res PCB pictures in their GPU reviews. Now, with that out of the way, let's get into it. And it's been so long since I've done one of these that I've forgotten where they usually start. So I guess we'll just sort of start with like random little things that are noteworthy about the card, like the fact that it has a BIOS switch, and it does have two BIOS chips, which are over here. So this means if you want to mess around with flashing various BIOSes onto this card, it'll be a lot safer because if you flash a BIOS that isn't compatible, you can just use the other BIOS. Also, by default, ASUS has like a quiet BIOS and like a performance BIOS. I don't actually know what the difference is. You can check the Tech Power Up review for that, because I don't really care. I mostly just see this as like a feature for messing around with BIOS flashing. So anyway, the card does have a BIOS switch. Then we have a bunch of minor voltage regulators scattered around the PCB that I don't know what all of them are. Even though ASUS has labeled all of the different voltage regions. So we have this over here, which might be PEX, might be 1.2 volts. I don't know. I don't have the card in hand. Then we have this over here, which I think might be 1.8 volts, but no idea. Yeah, actually no idea. It might be 1.8. It might be something else. This over here is PEX or 1.2 volts. Again, don't have the card in hand. Don't know. One of these is probably a 5-volt regulator, and there's maybe a 3.3 volt regulator as one. Yeah, like one of these might be a 3.3 volt as well. Or there's two 5-volt regulators, and then this thing that looks suspiciously like a linear regulator is a 3.3 volt regulator. And the reason that I'm like pointing all of these out is because ASUS does actually do this kind of neat thing on a lot of their newer cards, which is they label all of the different voltages. Unfortunately, we have like PEX VDD and 1.2 volts. That's just this read point over here, and PEX VDD is that one. GPU voltage is labeled here, 3.3 volt front panel. Actually, 3.3 volt front, or I actually don't know what the F stands for. Anyway, that's off the PCIe slot. Then we have 1.8 volts over here, 12 volts, probably off of the PCIe slot again. 3.3 volts, which I have no idea why there's a second 3.3 volt rail, but it's not the first time that I've seen one on an NVIDIA GPU. NVIDIA GPUs, for some reason, have extra 3.3 volt rails a lot of the time. Also, memory is labeled over there. So yeah, ASUS has all of these different voltage labels. They didn't label 5... Oh no, they labeled a 5 volt over here. But the issue with these, like, probe points that they've pointed out. Also, they've pointed out a ground point, though it's worth noting you can grab ground like this is ground. This side of these capacitors is ground. This is ground. Like, there's ground everywhere, so I'm not really sure why they're bothering to label a ground read point. But I guess if, you really struggle to identify grounds, I guess that helps. There's also a 12-volt external, which is the, the 12-pin... Wait. Yeah, 12-pin power... 16. I'm calling it the 12-pin. I don't care. It has 12 power pins. The 4 sideband things don't matter. Yeah. Or, well, they matter as much as the card decides that they matter. Anyway, yeah, so we have all of these, like, voltages labeled on the card, but they're all labeled down here. And on the front of the card, you might have noticed that, like, we have a bunch of voltage regulators up here. So that's why I don't know what everything is, because those voltage, like, read points are in a completely random location relative to all of the actual voltage regulators on the card. So thank you, ASUS, for making it possible to identify everything and check if all the voltages are actually present, right? That's kind of the main reason of having those labeled, is that if the card doesn't turn on, it's easier to figure out, like if there's like a power delivery failure, it's easier to figure out what part of the power delivery stopped working if you just have a bunch of labeled read points that you can measure. But I don't actually know which read points correlate to which regulators because they're not anywhere near each other. So anyway, that kind of covers a lot of the, like the minor voltage regulators. Another thing that ASUS has here is these unlabeled modification points, as well as what looks like an overvoltage jumper and a overvoltage LED. I guess NVIDIA would be very upset if ASUS actually labeled these, which is probably why they're not labeled. Because ASUS has like done this in the past on their on a lot of their cards that they'd give you like header, like through holes for modding the card, like for voltage control. But NVIDIA has kind of been, annoyed with manufacturers promoting any kind of extreme overclocking. So I guess that's why these aren't labeled, because historically ASUS would label them even on NVIDIA GPUs. So I'm not sure why they're not labeling them now. But anyway, those exist. Unfortunately, I don't know how they're wired up. So, yeah. Anyway, if you have an Elmore EVC2 or actually you probably want an EVC2. I'm not aware of anything. Yeah, I'm not really sure what you would use to control a monolithic power systems controller otherwise, but let's say you have an Elmore Labs EVC2. There's this header over here, which gives you a direct connection to the main voltage controller on the card over here. So if you want to use the EVC2 for voltage control, you would just hook that up here instead of like trying to connect directly to the I2C pins of the controller. And then there's a bunch of RGB garbage down here. Anyway, let's talk about the important power delivery, the stuff that actually like supplies the vast majority of the the vast majority of the power to the GPU core. So that's of course the Vcore VRM, which half of it is over here. So, and then the other half of it is over here. And the reason it's split in two like this is because it allows it allows you to push power into the core from both sides, which effectively gives you a much wider power plane cross-section, right? Because if you were pushing all of the power in from one side, your cross-section of the power plane would be just like basically this. I'm not actually sure how the BGA looks like, but you'll have like a lot of Vcore and ground, like you'll have a lot of Vcore pads directly under the chip, and I would assume there's also sort of more of them coming in sort of these areas. I don't have an actual pinout, but the chip is designed to get power from both sides, or like the package is designed to get power from both sides. And basically, if you had power from just one side, this is your power plane cross section, and that basically means that like limits how much impedance or how low you can get the impedance of the power plane, which limits how the impedance of the power plane sets how much power loss you get in the power plane. Also can affect the voltage regulation depending on how much inductance the power plane has. Well, if you have sort of two power planes, and I shouldn't be saying power planes, I should be saying power distribution network, because there's going to be multiple power planes, right? Like the 4090s, off the top of my head, I want to say use 14-layer PCBs. So there could be multiple Vcore power planes throughout that, across the layers. But anyway, with power coming in from both sides, you effectively double the cross-section of your power distribution to the chip, which means you can pretty much cut your impedance in half, right? Because it's twice as wide. So that's like a power delivery optimization. That's pretty typical of high-end GPUs these days because they just pull so much current. Didn't used to be a thing on older cards because they didn't pull that much current. Anyway, so that's why the Vcore VRM is split in two like that. As for the phase configuration, this is a 12-phase Vcore VRM, which is pretty typical for 14. Okay, I'm not going to do the dots manually. But each phase is basically made up of two power stages. Oh wait, I'm getting ahead of myself. I should have pointed out the controller first. So the controller for Vcore is this chip over here, which is the MP2891. This is a 16-phase controller from Monolithic Power Systems. Here it's running in a 12 plus 4-phase configuration. The plus 4 is for the memory. The 12 is for Vcore. Now, the card actually has 24 power stages on it in the Vcore VRM. So we have 2 power stages in each phase. Right, so like and I'm not sure how they're actually splitting the PWM signal up, but basically what they'd be doing is they'd take a PWM signal for one phase and they would just feed it into 2 power stages at the same time. So these 2 power stages would switch on and off at the same time, and they would act as basically one giant phase. which doubles your current handling capacity, but doesn't sort of affect the ripple, doesn't really affect the input like have any effect on the input ripple, compared to, like it switches like a 12 phase, right? There's 12 different phases of MOSFETs getting switched on and off, but you get 24 MOSFETs worth of current handling capacity, because the MOSFETs are all in parallel. So anyway, that's how the Vcore VRM is controlled and configured. Also, this is like basically the best voltage controller you can get for a 4090, and it is fully digital, which actually makes it kind of annoying if you don't have an Elmore EVC2, because hard modding, like with a potentiometer, the core voltage on, or really the core or memory voltage on the MP2891, isn't really viable, because the way this controller interacts with the PWM vid signal from the NVIDIA GPU core is that it actually measures the pulse width. So other controllers, like say the UP9512, would convert the PWM vid from the core into a like analog voltage level, and if you fiddle with that voltage level, you can control the core voltage. With this, it measures the pulse width, so you don't get to do that. And you really do need a actual you basically need some kind of way to write the registers on the chip to adjust the core voltage, because yeah, it's not analog like at all. So anyway, that's the control scheme for the Vcore VRM. In terms of current handling capacity, it is very, very powerful, which you would expect when you've got 24 power stages, and when those power stages are on semiconductor FDMF 3170s. Now, I'm kind of surprised to see this power stage on a 4090, because these are really, really old. The first card I've ever seen these on was, I think, the Titan V, but definitely these were common for like the 20 series, and we didn't really see any 30 series cards with them. So yeah, I am kind of surprised that we're seeing FDMF 3170s on a 4090, because these are like 20 series card power stages, but they were really, really powerful. Like, they are 70 amp smart power stages. There are more powerful and more efficient power stages available out there right now, but there's 24 of these. It doesn't really make much of a difference. And really, a lot of the power stages, once you go above like the 60 amp nominal current rating, a lot of them perform very similarly. Like 70 amp parts, 80 amp parts, 90 amp parts, 100 amp parts, they're all very similar. And no, you wouldn't actually want to run 70 amps through any power stage that's like nominally rated for 70 amps, because the efficiency is going to be absolutely atrocious. In fact, the documentation for these, which should be public, only goes to like, okay, actually these might go to 60, but it's pretty common for a lot of power stages to only, like even like nominally higher current power stages, to be spec'd only to 60 amps, because the efficiency once you're at the nominal current rating is so bad that you shouldn't be pushing them to their nominal current rating. Just, they get really, really hot. So in any real world design, this number is really not practical. This is more of a like performance class than it is an actual design target. You do not want to put 70 amps through a 70 amp smart power stage. It'll get very hot. And especially if you have, 12 of them right next to each other, it'll get way hotter. So yeah, anyway, they are still really quite efficient. And that means the following for the theoretical VRM efficiency of this card at 1.2 volts output voltage and 500 kilohertz switching frequency. Now, admittedly, 1.2 volts is way higher than what 4090s usually run on. They usually run at around like 1.1 volts. And that does slightly skew the power losses, like you'd have less power losses at 1.1 volts, though the efficiency would actually be worse. Generally speaking, with power stages, your efficiency gets higher as your output voltage goes up, but your overall power loss still slowly increases. So basically that means, like, say at 1 volt and 10 amps, you might dissipate 1 watt of heat, while at 1.2 volts and 10 amps, you might dissipate 1.1 watts of heat. So still technically more heat, but because you're pushing 12 watts instead of 10, and you're only dissipating, 1.1 watts of heat, like the efficiency is still higher. Anyway, also these efficiency numbers do not account for power losses in the inductors or in the, actually no, no, it doesn't account for power losses in the inductors, and it doesn't account for power losses in the power plane, in the power planes of the card. So yeah, these are estimates and really kind of about as useful as the nominal current rating of the power stages. So anyway, at 300 amps output current, this VRM should produce about 25 watts of heat from the power stages, which is very efficient. Basically, any VRM where, or at any, well, one lazy way to sort of judge the efficiency is if for a given current, the heat output is less than a tenth of the current, very efficient. So yeah, if you're, outputting 300 amps and only producing 25 watts of heat, these are, it's a very, like, that's well, like, that's in the good part of the efficiency curve for the power stages. Anyway, a 400 amps output current, the VRM should only produce about 34 watts of heat from the power stages, and we're going to put the 34 there. About 34 watts of heat. So also still very efficient. In fact, I think the efficiency here might be higher than it was at 300 amps, which is pretty common with really large VRMs like this, that they, like, basically because the efficiency curve is a curve that looks like this, if you have too many power stages, you end up in the bad end of the efficiency curve with very low heat per component. So the VRM won't run hot. It just won't be, hitting peak efficiency, which I think for something like these, it should be somewhere around 15 amps per power stage, because these are 70 amp nominally. Anyway, 500 amps output. Yeah, we're still getting really high efficiency, because that would only be about 43 watts of heat. I should have put efficiency numbers in my notes. Oh well, too late for that. 600 amps output, about 54 watts of heat, and 800 amps output, about 81 watts of heat. So yeah, at this point, well, like here we're talking like, actually, I think this might be doable on water cooling if you run like Furmark or something. In regular use, you should never really see 600 amps of current draw. But if you didn't have a power limit, I think Furmark might be able to hit that. And you'd also need water cooling because the chip will get incredibly hot. The 40 series has like a really high thermal density for a GPU. But anyway, at this point, we're talking like LN2 overclocking for 800 amps. And yeah, this VRM should handle that just fine. It's 2470 amp smart power stages, so that isn't particularly surprising. So yeah, a very, very powerful Vcore VRM on this card. Now let's talk about the capacitor configuration. And as far as I'm aware, this actually packs the most bulk capacitance of any 4090 PCB that I've seen. So you have all of these SP caps on the back, or at least I think these are SP caps. I'm not 100% certain, but these really look like SP caps. So, which are from Panasonic, and these are aluminum polymer SMD capacitors. These are basically the best bulk capacitors you can get from a electrical performance perspective. So lowest ESRs, lowest ESLs, which means they're really good at filtering the switching noise of the GPU core and the VRM. So yeah, we have all of these SP caps right off of the, coming like right off of the inductors. And in total, as I have counted them, no, I'm not normal, there's 35 of these. I wish I had schematics to tell me that instead of having to count them by hand, but yeah, so there's 35 of those, and they're 470 microfarads. I'm not sure what ESR and ESL spec they are, but honestly, when you have 35 of them in parallel, it doesn't really matter that much, as long as they're not, like, really terrible. And actually, the ESL isn't really a spec you would normally get for SP caps, but just the fact that these are, like, the ESL of a capacitor is heavily dependent on basically its physical shape. So just the fact that these are, SMD rectangular capacitors like this automatically means that they have an ESL advantage over CAN capacitors like these over here. Anyway, so yeah, on the back we have 35 470 microfarad SP caps, which is just a ton of capacitance in SP caps. Then behind the core, we have 470 microfarad SP caps, which is above the NVIDIA spec, as well as some multi-layer ceramics mixed in. I think the minimum required by NVIDIA for these is like 220 microfarads, but for some reason that isn't in my notes. So yeah. So ASUS has, I think ASUS has basically doubled the capacitance, like for bulk capacitance behind the core. And then we also have these like groups of 10 multi-layer ceramics over here. Oops. So yeah, I'm not sure on the capacitance of the multi-layer ceramics. These could be, like, they're probably 47s. I would hope they're 47s. It's a 4090. You know, they could use the nicer multi-layer ceramics. The most extreme scenario is that those are 100 microfarad, which, well, they could be, but usually the 100 microfarad multi-layer ceramics are, like, they exist, but they're real. I don't think, I might have seen a motherboard use them once, but yeah, not sure. And yeah, so I'm not sure what spec those are, but they are, like, from a ESR ESL perspective, they're a better option than SP caps directly behind the core. So I'm like, the thing is, the Founders Edition from NVIDIA, I think, only uses multi-layer ceramics directly behind the core. The issue is, without oscilloscope measurements, because of, like, everything else that ASUS has changed, I don't know how it would compare. So, like, I would expect this to have similar or better voltage regulation than a Founders Edition, but without measurements, I am not sure at all, because there's just too much that, you know, sort of goes into how the voltage regulation of the card behaves overall. Anyway, so this is like the higher frequency filtering stuff, right? The SP caps, the multi-layer ceramics. ASUS also just packed all of these like can capacitors on the front. I don't know who makes these. Yeah, I don't recognize this labeling at all. These are 820 microfarads. I have no idea why they're even here, because the bulk, like the SP caps on the back of this card alone, are more capacitance than what you'll find on most 49, like on, well, okay, I'm not going to say most because I've not counted, like, not done the math on that, but it's a lot of bulk capacitance just in the 35 SP caps that are on the back. And there's quite a few 4090s out there that'll have less total capacitance than just what this card has on the back of it. So why ASUS felt the need to add all of this, I have no idea, but they did. So yeah, the total capacitance on this card is actually completely insane, because these are 820 microfarads and there's 14 of them. Yeah, and for some reason my notes don't do the math, but you can just multiply the 14 times 820 and then 35 times 470, and that'll give you the total bulk capacitance on this Vcore VRM, and it's just insane. Like, it's a ton of capacitance. I think the Hall of Fame is probably the only card that has more, and Galax has, like, no chill when it comes to capacitor configurations, so that kind of makes sense. Anyway, so yeah, in terms of voltage regulation, I would expect this to be top 3 in among 4090s, if not maybe even the best. Anyway, so that's the output filter for the Vcore VRM, which is just huge, absolutely massive. Now let's talk about the input filtering, which is similar. So for input filtering, we have a lot of multi-layer ceramics, like more than what you would see on a lot of other 4090s, right? Like, ASUS just loves ceramic, so that's a good thing. Unfortunately, it doesn't give you that much capacitance, but the idea behind these is that these deal with the, like, beginning of the inrush of current when the power stages first turn on, because the switch on of the MOSFETs is pretty rapid. So the bulk capacitors are actually, like, these have too much ESL to sort of like really supply energy in that initial turn on of a power stage. So yeah, ASUS has just a bunch of multi-layer ceramics for that. And they have more on the back of the card. Yeah, like, there's just a ton of ceramic on the input filter on this card. I've not counted those. You know, I'm not gonna. It's too much. Anyway, But yeah, so that exists. And then we have, of course, the CAN capacitors. These are 270 microfarads each, 16 volts, which you'd expect on the 12-volt side of the card. And there's 12 of those in total, which is... My notes don't say if it's more than usual. I'm going to go it's probably more than usual, because it's an ASUS card. Like, the output filter's already nuts. Why wouldn't they, go kind of beef up the input filtering as well? Though I think this is not that, like, the output filter is just massive, but I think the input filter here, in terms of actual, like, polymer capacitors, isn't actually that impressive. It's more that they have a lot more ceramic in the input filtering compared to the other 4090s. And then on this side, we have a bunch of 56 microfarad SMD polymers, which are a weird choice for input filtering. Because aluminum, like, these are aluminum polymers, not tantalum polymers, which is why they're only 56 microfarads, because aluminum polymers don't really get high capacitance in high voltage ratings. And that's where you would sort of expect to see tantalums. Like, you could have 100 microfarad tantalums here instead. But considering the overall configuration of this, like, the input filtering generally isn't as important as the output filtering. And all of the extra ceramic that ASUS has mixed in, again, you would have to, like, it's interesting that ASUS basically has, like, compared to, say, a Supremax, this isn't that much input filtering capacitance. On the flip side, I'm pretty, like, you'd want an oscilloscope to actually measure if that makes a difference. Because with the input filtering really isn't that important, and this card does pack a lot of extra ceramic into the input filter, which is, like, impossible for me to judge what that actually leads to, because a lot of the time, like, input filtering just isn't that important unless it's massively under-spec'd, which doesn't usually happen with GPUs. But anyway, yeah, nothing to complain about, just sort of interesting design differences between the different manufacturers, in my opinion, and, like, how ASUS does their input filtering, considering how ridiculous their output filter is. Anyway, let's talk about the memory power delivery, which is so memory power delivery is this, oops, I'm circling it wrong. That, this, and also this. So we have the typical 4090, memory power delivery sort of all around the core, because the same idea as the Vcore VRM, right? You push power into the core from two directions to improve power plane impedance and reduce the power losses in the power planes. With the memory, we've got the same idea. You push power into the memory chips from all directions, and that improves the impedance of the memory power distribution and reduces power losses. So yeah, pretty typical for a 4090 to have the memory VRM laid out like this. Though not typical to have all four all four phases actually populated. A lot of cards will only have 3, if I remember correctly. It has been a really long time since I last looked at 4090 PCBs. So, but yeah, so pretty typical actual layout. For the power stages, we have more of the same FDMF 3170s that ASUS used on the Vcore VRM because, well, they already bought 24 of them. What's 4 more going to do? Consequently, the memory VRM is, like, massive overkill for the actual, like, the memory power delivery. And it is controlled by the same MP2891. It's the +4 part, this is like the standard way of implementing the MP2891 on high-end 4090s. Like, this is how the Supremax does it, the Founders Edition does it, and I don't think there's many other cards that use this controller, at least not any I can think of off the top of my head. So yeah, nothing, like, in terms of control and, like, configuration, this isn't anything, well, it's more powerful than what you'd find on a lot of other 4090s, because it's pretty typical to use, like, a 50 amp DR MOS instead of a 70 amp smart power stage. But if we're comparing, like, Supremax, Founders Edition, like the high-end 4090 PCBs, this is pretty standard, including the 70 amp smart power stages. Anyway, what's not standard is how much capacitance ASUS packed onto the memory power distribution. Like, we've got these two 470 microfarads over here. another 2 down here, and then you get to the back of the card, and we've got one here, and then we have some behind the memory chips, which is pretty normal, and then one there, and here, and then this blob over here, and this, and yeah. And in total, this has 18. Wait, 18. Really? Are my notes lying? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh yeah, 18, which is insane. I think normally it's like 9. Because normally you'd have like, yeah, you wouldn't have this, you wouldn't have that, you wouldn't have all of it. Well, no, you wouldn't have these two, you wouldn't have these two, and then you wouldn't have that, and you wouldn't have that. You'd basically have like one bulk capacitor per phase of memory power. And so, yeah, ASUS just, I guess they had a fire sale at the SP Cap factory because ASUS just covered the card in them. So I don't, the thing with the memory power delivery is memory usually doesn't pull that much power. And also isn't that hard on the voltage regulation consequently because it's not that power hungry. So, you know, with this, it's like, this is probably well into the territory of it doesn't actually make a difference. But without, you know, measuring with an oscilloscope, it's impossible to tell. This might have significantly better memory voltage regulation. It probably doesn't. And even if, or yeah, it probably doesn't. And even if it did, the memory, well, it depends what you're starting with, right? If the voltage regulation on like the bare minimum PCBs is terrible, and this is much better, then on average, this should have much better memory clocks. If the voltage regulation on the like bare minimum PCBs is relatively okay-ish, so somewhere under 100 well, I don't know. Like, you'd have to actually measure with an oscilloscope. It's impossible to say. But this is a lot of output filtering on the memory. Like, the most of any 4090 that I'm aware of. Yeah, probably the best in terms of memory voltage regulation. I'm just not sure if it's like a significant difference in terms of the memory clocks that you could actually achieve, or if it's just like we put capacitors because we have capacitors, more better, which is kind of what I think might be going on here because I don't know why they included all of these CAN capacitors because I don't really think they do anything, but they're there. So yeah, I guess that like if yeah, so that's kind of it. I can't see anything else in my notes, so I'm gonna go with that's it for the video. Yeah, so the 4090 Strix PCB from ASUS, very powerful Vcore VRM. Technically not the most powerful of the 4090s out there, but more than powerful enough for anything that you would want to do with a 4090, including LN2 overclocking. And then in terms of the filtering configuration, the output filtering on this card is massive. Just an absolute ton of capacitance on both Vcore and memory power. And then the input filter isn't as impressive as what you find on some other cards, but it does, like in terms of bulk capacitance, isn't as impressive as what you would see on some other cards. But on the flip side, ASUS has put a bunch of multi-layer ceramics in everywhere. So that might balance that out. Might actually end up being better overall because yeah, like the bulk capacitors don't necessarily handle the initial turn on of the power stages as well. But again, like you'd need an oscilloscope to actually measure what kind of effect these like design choices from ASUS have. They're certainly not cutting any corners though. Because basically, if there's a component that you would find on a 4090, there's either more of it, or it's better, or it's both, right? There's more of it, and it's better. So, yeah, a very, very nice, 4090 PCB from ASUS, and that's it for the video. So, thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's links to all of that down in the description below. If you check them out, that would be much appreciated. And yeah, that's it for the video. So thank you for watching, and goodbye.